All right, so we are looking at today intersections of lines in a two-dimensional scenario. Okay. Later, we'll talk about intersections of lines in a three-dimensional scenario. Okay. And what I tend to do is I open up the notes on all of these by listing off all of the possible ways that this could happen. Okay. And then I kind of draw like a little bit of a info thing in this area, and then we do a few examples. All right, and it tends to be sort of a guide for you in order to determine all of the ways that these things can unfold. All right, just kind of organizing these because there's a lot of information coming at you right now in these next few sections, and I'm going to try and organize it in a nice way here in these videos here. So we're going to start off with 2D intersections of lines. Now this is the easiest one, okay? And so it'll be nice because you'll kind of see how this notes flows, and all of the rest of them will sort of take on this format. So what types of solutions should we be ready for in these 2D intersections of lines? Okay. Basically, we could have infinite solutions. We could have one solution, and we could have no solutions. Infinite solutions is where the line 1 that we're talking about and the line 2 are actually the same exact line. So line 1 is actually equal to line 2. One solution is where these two lines just sort of intersect at a point, right? So our solution is a point, some x, y coordinate. No solutions would be a scenario where line 1 is parallel to line 2, okay? And so how do you determine which of these you have? Well, if my lines are in scalar form like this, okay, then if they're equal, then the A over the A divided by the B over the B divided by this C over the C are all going to be equal. So A1 over A2 equals B1 over B2 and equals C1 over C2, okay? So basically what I'm saying is if they're in scalar format, these guys are the same, all right? The ratios. Whereas likewise, if they're parallel, A1 over A2 is going to be equal to B1 over B2, but the C1 over C2 section will not be equal, okay? So these two scenarios are pretty easy to determine right off the bat if they're in the scalar form, okay? I'll talk about vector form as well just shortly. So you can kind of, by the way, what does this stuff mean? Well, if A1 over A2 is equal to B1 over B2, that guarantees that the lines are parallel. Then if the C1 over C2 are also equal, that means that they've been pushed in the direction of their normal, the same distance from the origin, okay? And here, if A1 over A2 is B1 over B2, they're equal, then they're parallel. But if the ratio of their C values is not equal, then that means one has been pushed a certain distance, but the other one has been pushed a different distance, effectively making them not equal lines, but parallel lines. Over here, they're actually would be the same exact line, but written slightly differently. So you might be asking yourself, how could I have the same line, but written differently? Well, if, for example, this is like a 2, a 2, and a 2, and that's like a 3, a 3, and a 3, then you effectively actually have the same line, okay? And we'll see that in some examples as they unfold. Whereas, okay, so now let's talk about the middle possibility. If you have basically two lines that are not parallel and not the same exact line in two dimensions, they guaranteed intersect at one location. This is now, again, in a two-dimensional scenario. Basically, you know that that's the case if the A1 over A2 is not equal to the B1 over B2. And the C values actually don't have anything to do with this. So basically, you have all of these different variations, okay? Question is well, what happens if I've got a vector form, okay? In the vector form, you would actually use the slopes, the ratios of the slopes here, instead of the ratios of the A, B's, and C's, okay? So let me go ahead and do maybe sort of a green. Well, I've already used green. Let me do blue here. So in the vector equations, basically you would take these ratios, and we'll call that basically M1 is parallel to M2 here, and M1 is parallel to M2 here, okay? Whereas over here, M1 is not parallel to M2, all right? But then that sort of begs to ask the questions, well, what's the difference between these two, here and here, okay? If you're in vector form, you check your slopes, and they happen to be parallel. You still don't know whether or not you've got this or you've got this. So now at that point, what you do is you take a point from one line and you plug it in as the solution to the other line. And if you get a solution, then you have this. If you don't get a solution, you have this. And so I'll write that down. Here is P1 is a solution in line 2. All right. Oh, I should have written that in blue. Sorry. Here, P1 is a solution in line 2. And here, P1 is not a solution in line 2. And you might be asking yourself, well, what do I mean by is a solution? Remember those examples previously that we did? How do we determine if a point is on a line? You would do that. You would basically take this point and you would test to see if it's on this line. And if it is, then you know you have the same line over here. If it's not, then you know you have no solutions, okay? So basically, what I've done here for us is I've laid out all of the three possibilities, okay? I've drawn pictures of them, all right? And if they're in a scalar, right? If the equations happen to be given you in scalar format, then you would sort of take this approach. If they happen to be given to you in vector format, you would take this approach here, okay? So let's do a few examples, all right? Here we go. First of all, I'm going to see if the ratios of my A, B's, and C's give me any kind of information here. Well, they're always going to give you my information. So I got 4 over 6. Is it equal to a negative 6 over a negative 9? Okay, well, 4 over 6 is about 0.6, okay? And negative 6 over negative 9 is also about, it's 2/3, right? So I divide that by 3, I get a 3. Divide that by 3, I get a 3. No, 2, whatever. Divide both of these are equal, right? Is what I'm trying to say. Question is it equal to this as well? Negative 10 over negative 15. Oh, that actually is also a 2/3. So this is 2/3, that's 2/3, and that's 2/3. So as it turns out, I actually meant to write find the solutions to the following systems. The solution is that these two lines are exactly the same line. And so therefore we have an infinite number of solutions. Each one of the points on every line is, so we would say that line 1 is equal to line 2. There are an infinite number of points that these two lines share. Okay? Okay, so now let's talk about the vector equations. First off, I want to test to see if the two slopes are parallel, okay? For example, and I know if they're parallel, then I either have this scenario or that scenario. If they're not parallel, then I have this scenario, okay? So let's go ahead and figure out if my two slopes are parallel here. My slopes are here and here. So I'm going to do negative 6 over 9. Is it equal to 8 over negative 12? What is this? 2/3 and 2/3. Shoot, it is. They are equal. So therefore, I know that line 1 is parallel to line 2. But are they the same line? I don't know. So I have to determine if they're the same line. So now what I do is I take 1, 5, and I plug it into this line here. And I'm going to use the parametric format. So I'm going to do x and y is equal to 1 and 5, which is equal to 2 plus 9s, 2 plus 9s. And then I'm going to get 1 plus a negative 12s, or 1 minus 12s, right? This s, you know what, I don't like that s, so I'm going to change it to an m because it looks like a 5. I'm going to change it to an m and an m. So now the question is 1 and 5, is 1 comma 5 on this line over here? What I'm doing is I'm trying to determine if P1 is or is not a solution to line 2. So here's line 2, here's P1. It's, by the way, P1 is the point on line 1. I think I'd never mentioned what P1 is, but P1 is the point on line 1. So how do I determine if this is on there? Basically, if M is the same here and here, then I know that 1, 5 is a solution, okay? Well, let's solve for M in both of these cases. So I'm going to subtract 2, and so I'm going to get negative 1 over 9. Negative 1 over 9 is M. Over here, I'm going to subtract 1, and so I'm going to get 6. So, sorry, I'm going to get 4 over negative 12 is M here. Okay, well, the M in the X and the M versus in the Y components, they are not equal. So the parameters are not equal here. Okay, I don't want to put subscripts there. So the parameters are not equal. So therefore, 1, 5 is not on the line. So therefore, 1, 5, 1, 5, 1 comma 5 is not on the line 2, but the lines are parallel, right? But line 1 is parallel to line 2. So the overall final conclusion is that there are no solutions. All right. And that's how you do that one. Okay. I guess I don't have an example where there's just one solution. I'll make one up. All right. I'm going to make one up where it's this middle section. All right. So I'm going to give us a line 1 and a line 2. And it's going to be x, y, x, y. I'll give them in vector form. And I'll just do like 2, 3, 1, 0. Let's do something simple here. Plus t at 1, 1, and plus m at 2, 3. All right. Let me, I'll change that as put that as a plus here. Plus. Okay. So now I'm gonna again. I know this is going to be in the middle, a one solution, but I'm going to test it anyway. So first thing I do is I know I'm vector form, so I test the slopes here. Is 1/2 equal to 1/3? No. Okay. So 1/2 is not equal to 1/3, and so therefore line 1 is not parallel to line 2. So I have to have a single point solution. All right. So therefore, how do I find that solution? What you do is you actually take the parameters for x, all right, and you set them equal to each other. So I'm going to do 2 plus 1t, okay, 2 plus 1t. And I'm going to set that to the parameter. Sorry, I said parameters for x. I meant the components for x. I'm going to take the x here, and I'm going to do 1 plus 2m. So equals 1 plus 2m. And what I'm doing here is I'm basically taking the x components and setting them equal to each other because I know that they have some sort of x value in common, and they also have some kind of y value in common. Why do I know? Because they're not parallel. And in 2 dimensions, like we said before, if 2 lines are not parallel, they must intersect at some location, and therefore I know that if they intersect at one location, I know that there is one XY coordinate pair that they have equal. So I'm trying to find the X that they have equal at the same time that they have a Y equal to each other. And so I'm going to go ahead and set their Y's equal to each other. So the Y component is 3 plus 1t. All right. So 3 plus 1t. And the Y component here is 0 plus 3m, right? So equals 0 plus 3m. And now you kind of just take these 2 sections here and you say, look, I've got 2 equations, and in each equation there's a t and an m and a t and an m. So what I can do is I can solve for m in this one and plug it in here, solve for t, and so forth. Okay? So I guess I'll take maybe this equation, solve for m, or you know what? Actually, I'm going to solve for t. Look at how easy this is. If I subtract a 3 over here, I'm going to get t equals 3m minus 3. So in the y equation, I'm going to get t equals a 3m minus 3. Is everybody okay with that? So notice what I've done is I've written this y here as well. All right. I want you to start keeping everything really organized in these questions, right? Because what's going to end up happening is you're going to have a lot of little lines all over the place flying around, and you're going to have an hour and 20 minutes to do a test, and your organization is going to be key. Okay. And so what I do is every time I take a formula, right, and I sort of maybe rearrange it, I always try and, like, if it's the y formula, I write a little y there and an arrow, right? Or a colon or something like that. I can't write equals here because it's not that y equals t, because y equals 3t. So I can't write y equals t. But I can just remind myself that I've used the y formula, okay? Now, in the x formula, I'm going to write 2 plus t, but remember, t is 3m minus 3, should equal 1 plus 2m. Okay, and now look at this. This is spectacular. I have just a single m in this equation, and that's it. Well, I have two m's, but I can get it together here. And so I'm going to basically, what am I going to do? I'm going to pass my number over here and this m over there. And so I'm going to get 2 plus, I'm going to get 2 minus 3 minus 1 equals 2m minus 3m. And let's, hopefully I'm doing this right. What's 2 minus 3 is negative 5. This is negative 4, negative 2 equals, what's this? Negative 1. M divided by a negative 1. Oh, it looks like m equals 2. All right. M equals 2. Right. And now I'm going to take line 2. All right. And I'm going to say x equals, right, 1 plus m times 2, and y equals 0 plus 3m. I'm going to write a 2m here. This is just the parametric equation, but I've discovered that m equals 2, okay? So instead of these m's, I'm going to write down 2, all right? There it is, and there it is. And what I'm actually getting is I'm getting an x and a y coordinate that corresponds to the m that I solved for previously, okay? You might be asking yourself, what about the t value? It turns out I actually don't need the t value, but I'm going to use it anyway in just a moment, and I'll show you. I'm going to solve this anyway. I'm going to get 5, and I'm going to get 6. And so the coordinate where these two guys intersect is x coordinate is 5, and the y coordinate is 6. All right. By the way, if m equals 2, then t equals 3 times. Hold on. Let me do this in a different color. We're now done with the question, but I'm going to verify this. I'm going to verify this with purple, maybe. How about purple? I'm going to use a color I haven't used in a while, just to sort of spice things up. Orange. I'm going to use orange. So hopefully you guys can see this. It's, where is it at? Where is it at? I'm going to do 3 times 2 minus 3. So what I'm saying is if m equals 2, then t equals, what's 6 minus 3? It was 3. Well, then t equals 3. Well, now what I'm going to do is I'm going to take the t components here. If I put a 3 here, what's 3 plus 2? It's 5. If I put a 3 here, what's 3 plus 3? 6. Bam, look at that. I get the same answers, 5, 6, okay, for my t value of 3. So when t equals 3, this line has a point on it that's called 5, 6. And when m equals 2, this line here, the other line, line 2, has a point on it called 5, 6, right? So this is when m equals 2, and this is when t equals 3. And so therefore, the point that they share is 5, 6. And so therefore, these guys intersect at 5, 6. So I would say there's one solution, and it is at 5, 6. Yeah, we'll do that. We'll leave that at that. Good job, everybody. Let's go with